Hello everyone. So today I'm presenting my project on convolutional autoencoders for visual data retrieval and compression. So my teammates are Abhishree and Ruchika. Our motivation for the project was that mostly images have metadata which is inconsistent and bad, which leads to poor compression, poor image retrieval. So we try to mitigate it by using autoencoders. Autoencoders can be used to compress the data to the latent space, and the vectors in the latent space can be used to retrieve the data efficiently. For as they will as the images as the vectors in latent space will be closer to each other. Similar images will be closer to each other. So we are using convolutional autoencoders. It has two parts, encoders and decoders, and we are using mean squared error for the loss. The datasets we are using are MNIST and LFW deep funnel dataset, which has faces of people along with the names. The input should be the raw images, and the output should be latent space representation of that image, as well as if we give a query image, then top k similar images based on the query. Um, so for our methodology, we did pre-processing by normalizing and batching the images. For the model, we are using convolutional autoencoders, which has a latent space representation of which first compresses the image representation into a smaller vector and then expands on it. And then KNN for nearest neighbor for similarity search. We have used Adam optimizer, and evaluation metrics are reconstruction loss, precision for the top K images, mean average precision, and mean reciprocal rank. So for our baseline, it had around 0.75 precision for the top 10 similarity search, which was pretty bad. And these are some of the examples of the reconstruction. So we tried to, as this model was autoencoder, we tried to improve on it as we are using images to by using convolutional autoencoders instead of normal autoencoders. Uh, this is the graph of validation loss versus the epochs. So uh, as we can see, the we decided on using the 16 dimension latent space vector as it has the best trade-off between space and the reconstruction error. So the following examples will be the performance of the 16 dimension latent space vector. For the retrieval metrics, the as you can see, as the epochs keep on going, the all the precisions keep on like improve, such as the precision for the top 1 to top 10, mean average precision, and as you can see, the second graph is the retrieval of that digit class. The similarity of the that digit class, and the lower image is the query image. If the first is the query image, and the images next to it are similar retrieved images. This is the confusion matrix for our project. So as you can see, it does not perform well in only 5 and 9, as these can be in 4 and 5, as these can be confused with 3 and 9 respectively. So it is pretty understandable, as the images in MNIST are pretty weird at some places. So uh, these are the reconstruction images. As you can see, the reconstructions are pretty well, and the Errors are in insignificant places, so it should be fine. And the compression ratio is also pretty well. We also used uh, the faces dataset to check how the model performed in general. So as you can see, the reconstructions are also pretty well for uh, the latent space vector, which was around 1024. And the similarity search, as you can see, also learned pretty well. So it learned how to classify between old men wearing suits and blonde women with blonde hair. So that is also pretty nice. And the challenges we can improve on the by improving the performance of the faces dataset, having more variation in the dataset, and these are the references: MNIST dataset and the faces dataset. Thank you.